Okay, so let's dive into this bone marrow research you sent over. Honestly, I never really thought about what happens to bone marrow during surgery, especially when the surgery itself involves bones. But apparently there's this whole thing with tiny bone marrow particles called emboli traveling to the brain. And there's a new way to actually watch this happening live.
It's actually, you're right. It's way more common than any of us thought. This research used, well, they used this really advanced ultrasound technology. It's called Doppler, and they were able to use it to track those tiny emboli in real time during surgery. Well, before this, we were basically operating blind when it came to these tiny particles, you know?
Wow.
It's pretty groundbreaking stuff.
So to do this, they use pigs for this study,
Mm-hmm.
which I got to say, that seems, well, it seems a little out of left field.
I can see why you'd think that. But think about it this way. Pigs are surprisingly similar to us, anatomically. Like, they're practically the stunt doubles of the human body when it comes to this kind of research. Plus, for this study in particular, using pigs meant the researchers were able to see how these emboli traveled without having to worry about the lung filter that, you know, can sometimes complicate things in humans, especially with certain heart conditions.
Interesting. So it's like having a clearer picture of the emboli's journey as they move through the bloodstream without any detours. What kind of surgeries did they do on the pigs?
They focused on a procedure that's actually quite common in orthopedics called reaming and nailing. And here's the really interesting part. They found that this procedure caused those emboli to travel to the brain, even in pigs without any holes in their hearts. And that's a big deal because before now, a hole in the heart was seen as the biggest risk factor for this kind of thing, you know?
Wow. So this research is really turning what we thought we knew on its head. So does this mean that even routine orthopedic surgeries, like the kind that people get all the time, could come with a risk of these emboli reaching the brain?
That's exactly what it means. And that's why this research is so, well, it's a game changer, really. It could completely change how we look at risk assessment for even these common procedures. It's like, suddenly realizing there's this whole other layer of things to think about that we hadn't even considered before.
Okay, so we've got these tiny bone marrow particles potentially going places they shouldn't be during surgery, which is, I have to say, it's a little unnerving. But didn't they also look at this in humans at all? I thought I remembered something about them looking at infants undergoing heart surgery.
You're right. They did look at infants who were having heart surgery, specifically surgeries that involved the breastbone. And what's really fascinating is that they found a really similar pattern of these emboli being released during those surgeries, just like they saw in the pigs. But the intensity of the signal, basically how those emboli showed up on the ultrasound, it was different in the infants.
So same journey, different signal strengths. Why is that? Is it that babies, like their bones, release different kinds of emboli or something?
So it might actually have to do with what makes up their bone marrow. See, infants, they have almost zero fat in their bone marrow. It's pretty much all hematopoietic elements, which is the stuff that forms blood cells. It's like, comparing a really thick milkshake to like skim milk. They're both milk, but what they're made of and how they, like, the consistency is different.
So the fattier the bone marrow, the more noticeable these emboli are on the ultrasound. That's pretty wild.
Yeah, it's kind of like we're seeing like echoes of what our own bone marrow is made of. It's pretty cool.
Oh, it is. It really is. So speaking of uncovering things, the study did mention that this new ultrasound, this Doppler, it's got some limitations, right?
Yeah.
It's something about it being hard to tell different types of emboli apart.
Right, yeah. So they found that while Doppler is really, really good at picking up these tiny emboli, even with how high frequency it is, it's not always easy to tell if the signal is coming from a solid embolus, like a piece of bone marrow, or if it's a gaseous one, like just an air bubble.
Oh, okay. So it's like you might see a blip, but you don't necessarily know what that blip is made of.
Exactly. The researchers actually pointed this out specifically. Even with this single-frequency Doppler ultrasound, as advanced as it is, you can't just look at the signal and say for sure whether it's a solid or a gaseous embolus. They both create these similar blips,
Yeah.
They're called high-intensity transient signals, or HITs.
HITs, got it. Okay, so how were they able to tell what was what in the study then? Or is that still a mystery?
Oh, they came up with a pretty clever way to do it. So in the pig study, remember they were looking specifically at bone marrow emboli, right? So what they did was they injected a few different things into the pig's carotid artery while they were watching everything with the Doppler.
Oh, interesting. So like a comparison to see what each thing looks like so they'd know what they were looking for.
Yeah, exactly. They used, they used a few different things, like an agitated saline solution, which makes those micro bubbles, and even like actual bone marrow. And by doing that, they could see the different patterns each thing made on the ultrasound, kind of like creating a reference point for each one. And and it wasn't just the visual patterns. They were also analyzing like how intense the signal was. For example, they found that when they injected the saline, the signals were a lot more intense than when they used the actual bone marrow.
So they basically made their own like emboli dictionary using the ultrasound.
Right, exactly.
That's really, really clever. But it kind of sounds like, I don't know, we're still in the very beginning stages of really wrapping our heads around all of this, huh?
I would say so, yeah. There is still so much more to learn, especially when it comes to what these emboli are actually doing in the long term. Particularly when you factor in different types of surgery. And then, of course, everyone's different. So how those individual differences play into all of this. Plus, there's refining the technology itself and coming up with even more sophisticated ways to actually analyze those signals. It's a lot.
Yeah, for sure. And of course, the big question, if it turns out that these tiny emboli really are causing problems, is there anything we can do to, like, stop them?
Well, that's the hope, right? But this research is really just that first step. Now that we can actually see these emboli, thanks to Doppler, we can actually start asking those questions. Like, are there certain techniques that are more likely to cause them? Can we, like, tweak existing procedures to maybe, I don't know, minimize how often they happen? These are the really exciting possibilities this research opens up.
Yeah. So potentially safer surgeries down the line, and it's all thanks to, like you said, a deeper understanding of these tiny travelers. That's really reassuring. But you mentioned they also looked at emboli during heart surgery in infants, right? Did they do those same kind of injections with them?
They didn't. Remember how the infant part of the study was really focused on just observing the emboli during that one specific part of the surgery, the sternotomy, when they're opening the breastbone? Well, ethically speaking, doing those injections like they did in the pigs, that just wouldn't have been right in human infants.
Oh, right, of course, yeah. That makes sense. But they still saw those, what are they called? Those HIs. They still saw the emboli signals during those infant surgeries, right?
Mm-hmm.
And they were able to compare, like, how intense those signals were to the ones from the pigs.
Exactly. And that's where it gets even more interesting, actually. Remember how we were talking about those signals from the infant heart surgeries, how they were less intense than the ones from the pigs?
Right. Right. And we thought it might be because infants have less fatty bone marrow, but that was mostly just a guess based on, what we know about bone marrow generally.
Exactly. But here's what's really interesting. The researchers, they noticed something else in the infants that, well, it actually seems to support that idea. See, 2 of the infants had a particularly high number of H heights during their sternotomies. One of them had transposition of the great arteries, meaning the 2 main arteries that leave the heart were switched. And the other infant had a kind of heart defect called a transitional atrioventricular septal defect.
Okay, so 2 different heart conditions, but both requiring surgery. What's the connection to the emboli?
Well, both of these conditions can actually change the way blood flows through the heart, like literally change the patterns of blood flow. And remember, the researchers were really interested in the emboli that end up reaching the brain. So if the blood flow is different, if it's easier for those emboli to kind of, I don't know, bypass certain filters like the lungs,
then it's more likely they'll show up on the ultrasound and get to the brain.
Yeah.
Like taking a detour on a road trip, that helps you skip over, like a big city.
Exactly. So, for example, in the case of the infant who had transposition of the great arteries, the researchers, they noticed that their venous blood, which would be carrying any emboli from where they did the surgery, it would actually bypass the lungs completely before it even started circulating through the body. And that could be why they saw more of those HATs.
Wow. So it's not just about what the bone marrow is actually made of, but also about each person's, like, their own individual anatomy and how their body works. Like, each person adds another layer to how these emboli travel. That's really interesting.
It is really interesting, and it's actually a perfect example of why this entire area of research is so important. We're like finally starting to see these things that have probably always been happening during surgery, but we just we had no idea. And it makes us think differently about risk, surgical risks. It's not just about the procedure itself. It's about the entire patient, who they are, what they're made of. It's really fascinating stuff.
It really is. This is a lot to take in. I mean, we've gone from bone marrow to ultrasound technology to those mysterious HIs, and now we're like talking about cardiology.
Yeah.
So, okay, let's see if I can sum all this up. We started with bone marrow, right?
Yeah.
And it turns out it's not just like hang out in our bones. It's actually releasing these tiny emboli, especially during surgery. And we're talking even routine surgeries, right? Not just like major stuff.
Right, exactly. And what's amazing is that we can actually see these emboli now, in action thanks to this new ultrasound technology, this neo Doppler. I mean, it's incredible. But I have to admit, it's a little, I don't know, a little creepy too, right?
Yeah, a little bit. Like
Yeah.
we're seeing all these things happening inside us that, we had no clue about before. But thinking about the research as a whole, it really highlights something we all kind of take for granted. I mean, the lungs, right? They act like a filter for our blood. It's wild how our bodies just like have these systems in place to protect us. But this research shows that even those systems aren't perfect. I mean, especially during something like surgery when, everything's disrupted.
You're exactly right. It really makes you appreciate just how complex our bodies really are, doesn't it? And, it also shows just how important this kind of research is. I mean, just imagine if we could come up with new ways to do surgery or even like ways to keep these emboli from forming at all.
That would be, I mean, talk about a game changer. This whole deep dive into the world of bone marrow has been, well, eye-opening is an understatement. It's not just like this boring, inert material. It's active, it's dynamic, and it's involved in things we're just like starting to understand.
And the best part is, now that we have these tools, like this high-frequency ultrasound, we can finally see what's really happening. It's like we've been in the dark this whole time, and now we're finally able to shine a light on these things. And who knows what we'll find, right? It could completely change how we think about surgery in the future.
It could, absolutely.
Yeah.
It's like we've opened the door to this whole new world of surgical insight. And you, all of our amazing listeners, you're right here on the journey with us. That's it for this deep dive. We'll be back soon with more. Until then, stay curious.